Somewhere out there, the universe is broadcasting signals we've never been able to hear. Faint ripples from black holes that merged before Earth even existed, and whispers from a substance that makes up most of everything around us. Yet we've still never directly detected it. In July 2026, a team in London built a prototype device that just proved we finally have a way to actually hear those signals through the noise. Stick with me, because this is one of those quiet breakthroughs that barely made headlines, but could end up rewriting what we know about the universe over the next decade. If you want to understand exactly how it works, hit subscribe now, because we're about to break down one of the most important quantum physics results of the year. Let's start with the basic problem scientists have been stuck on for years, because you need to understand this before the breakthrough actually makes sense. Two of the biggest unanswered questions in all of physics are, what is dark matter actually made of? And where are the gravitational waves from the earliest moments of the universe hiding? Dark matter is the invisible substance that appears to make up the vast majority of all matter in the universe. Based on how galaxies move and hold together, yet nobody has ever directly detected a single particle of it. Gravitational waves are ripples in space itself, produced by some of the most violent events in the cosmos, things like black holes and neutron stars colliding together. Both of these mysteries share the exact same core problem the signals scientists are searching for are incredibly, almost impossibly faint. And they can easily disappear underneath ordinary background noise before anyone even has a chance to notice them. To really appreciate why these two mysteries are treated as such enormous priorities across the entire field of physics, it helps to understand just how much of the universe we're actually talking about here. When astronomers measure how fast galaxies rotate and how galaxy clusters stay gravitationally bound together instead of flying apart, the numbers simply don't add up. If you only count the matter we can actually see through telescopes, stars, gas clouds, planets, and everything else made of ordinary atoms, there has to be considerably more mass out there holding everything together, mass that doesn't emit, reflect, or absorb light in any way we've ever managed to detect directly. Scientists have been searching for this missing matter using dozens of completely different experimental approaches for decades now, underground detectors buried deep beneath mountains to shield them from cosmic ray interference, particle collider experiments, and increasingly, precision quantum sensors. Exactly like the one at the center of this story. Every single search so far has come back empty-handed on a direct detection, which is exactly why finding a genuinely new detection method, one capable of reaching sensitivity levels nothing else has managed before, generates this much excitement among physicists. One of the most promising tools scientists have for chasing down signals this faint is something called a long baseline atom interferometer. Here's how it actually works. You take a cloud of ultra-cold atoms cool down to temperatures just barely above absolute zero, and you use precisely controlled lasers to split that cloud apart and then bring it back together again. As the atoms travel along their slightly different paths before recombining, they behave like waves. And any tiny disturbance along the way, even something as subtle as a passing gravitational wave or an invisible dark matter field, can leave a measurable fingerprint on how those atom waves interfere with each other when they come back together. It's an extraordinarily precise measurement technique, sensitive enough in theory to catch signals nothing else on Earth could detect. But there's a catch, and it's a big one. The very laser used to control and measure these atoms generates its own background noise, called phase noise, and that noise is often far stronger than the actual signal scientists are hunting for. Imagine trying to hear a single, extremely faint whisper from across a massive stadium, except the microphone you're using to listen also happens to be blasting static directly into your own ear the entire time. That's essentially the challenge, facing every atom interferometer, trying to detect something as subtle as dark matter or an ancient gravitational wave. Without a way to strip out that self-generated noise, the signal researchers actually care about simply gets buried and becomes impossible to see. Scientists have had a proposed solution to this problem sitting on the table for years, comparing two separate atom interferometers running side by side, both hit by the exact same laser and therefore the exact same noise, and then mathematically canceling that shared noise out, leaving only the differences between them, which is exactly where a genuine physical signal would show up if one exists. The idea made sense on paper, and it forms the foundation of essentially every future large-scale detector design currently being planned around the world. The problem was, nobody had ever actually proven this idea works outside of a clean, idealized theoretical calculation, until now. A team based at Imperial College London, working as part of a UK-wide collaboration called AION, the Atom Interferometer Observatory and Network, finally put this concept to a real physical test. Their research was published in the journal Nature, meaning it went through full peer review by independent experts before being released publicly, giving it real scientific credibility rather than just being a preliminary announcement. To run the experiment, the team built a tabletop setup inside Imperial's ultra-cold strontium laboratory, using two separate, widely spaced clouds of ultra-cold strontium-87 atoms, both measured using a single, extremely stable clock laser. This setup was specifically designed to mimic the exact conditions expected inside future, much larger detectors, where controlling noise becomes an increasingly serious engineering challenge as the instruments scale up in size. Strontium-87 might sound like an oddly specific choice of atom to build an entire experiment around, but it's actually become something of a gold standard across precision physics in recent years, and for good reason. Strontium atoms have an extremely narrow, extremely stable internal transition, essentially a very precise internal frequency the atom naturally oscillates at, that makes them ideal for building some of the most accurate atomic clocks ever constructed. Clocks so precise they wouldn't lose or gain a single second over the entire age of the universe. That same property, an incredibly stable, well-defined internal reference point, is exactly what makes strontium atoms so useful for atom interferometry too, since the whole measurement technique depends on tracking incredibly subtle changes in how these atoms behave with extraordinary precision. Cooling the atoms down to temperatures just barely above absolute zero, colder than the depths of space itself, strips away nearly all of the random thermal jostling that would otherwise interfere with the delicate measurement, leaving researchers with an atom cloud that behaves almost exactly the way clean quantum theory predicts it should. To really put their idea through the ringer, the researchers didn't just run a clean, easy test. They deliberately pumped in a huge amount of extra phase noise into the system, far beyond anything a normal, well-behaved clock laser would ever produce on its own. Under those brutal conditions, each individual atom interferometer, tested completely on its own, became essentially useless. The delicate interference pattern the whole measurement depends on was totally buried underneath the artificial noise the team had intentionally added. If you only looked at one interferometer's results by itself, you would have concluded the entire experiment had failed. But then came the actual test of the theory. When the researchers compared the two interferometers against each other instead of looking at either one alone, the real signal reappeared, clearly and reliably. Each individual measurement still looked like pure random noise on its own, but the relationship between the two datasets revealed the system's genuine underlying behavior. And here's the number that really matters. The combined result reached what's called the fundamental quantum limit. Essentially, the theoretical best possible precision physics allows for a measurement like this. That's not a partial success, that's confirmation. The underlying concept works exactly the way theory predicted it should under real, imperfect, noisy experimental conditions, not just in a clean simulation on a computer. The team didn't stop there either. To make the test even more meaningful, they deliberately added a separate artificial oscillating signal into the experiment, deliberately designed to resemble what a real passing gravitational wave or a genuine dark matter field might actually look like if one were truly present. And here's the exciting part. Even in situations where neither individual interferometer produced anything useful on its own, drowning completely in the artificial noise, that added signal remained clearly detectable once both interferometers were analyzed together using the noise canceling technique. In other words, this wasn't just proof that the noise cancellation trick works in theory, it was direct proof that a real signal, buried under overwhelming interference, can be successfully pulled out and identified using exactly this method. Dr. Charles Bainham, who co-leads the ultra-cold strontium laboratory at Imperial College London, explained why this moment actually matters so much. According to him, scientists have known for a long time that quantum sensors could eventually help us understand the universe better. But it's only relatively recently become genuinely possible to build them with enough resolution to actually make that promise real. He described the team as immensely proud of the work that went into making these sensors an actual working reality, and said he's personally looking forward to the day when signals picked up from a single atom can tell us about a black hole merger that happened millions of years ago, an event we'd otherwise have absolutely no way of ever detecting. Dr. Richard Hobson, the other co-lead of the same laboratory, framed the achievement in a similarly striking way. He pointed out that the team essentially took some of the most precise scientific instruments ever built, atomic clocks and atom interferometers, and demonstrated they can be repurposed into something new, opening entirely new windows onto the parts of our universe that remain completely invisible to us right now. He was careful to note that their current setup is genuinely just a prototype, a proof of concept rather than a finished detector, but he emphasized that scaling this exact approach up into a full-scale facility, potentially built at major research institutions like CERN or Fermilab, could eventually let scientists tackle some of the deepest, most stubborn mysteries in all of physics, including finally pinning down exactly what dark matter actually is. It's worth understanding just how big a scale we're actually talking about here, because this prototype sitting inside a university lab in London is really just the very first smallest step towards something considerably more ambitious. The AION collaboration itself brings together researchers from Imperial College London, along with the universities of Birmingham, Cambridge, Liverpool, King's College, and Oxford, plus the STFC Rutherford Appleton Laboratory, all working together under one coordinated UK research program. Funding for this specific work came through the Quantum Technologies for Fundamental Physics program, a joint initiative between two of the UK's major research funding bodies, specifically set up to support exactly this kind of ambitious, long-term quantum sensing research that wouldn't necessarily attract funding through more conventional, shorter-term research grants. Coordinating a project across 6 separate universities and a national laboratory is genuinely no small logistical challenge on its own, even before you factor in the actual physics involved. Different institutions often specialize in different pieces of the overall puzzle. Some groups focus heavily on the ultra-cold atom physics itself. Others specialize in the precision laser systems needed to control and measure those atoms. And still, others focus on the theoretical modeling needed to predict exactly what a genuine dark matter or gravitational wave signal should actually look like once it's finally detected. Bringing all of those specialized pieces together into one coherent working prototype and getting a result solid enough to clear the rigorous peer review process required for publication in a journal as selective as Nature represents a genuinely significant coordination achievement in its own right, well beyond just the underlying physics breakthrough itself. And AION isn't operating in isolation either. It's directly connected to a much larger international effort that includes close collaboration with a similar project called MAGIS, based at Fermilab in the United States. Together, these two programs are pushing toward building genuinely large-scale atom interferometers, specifically designed for fundamental physics research that simply isn't possible using any other existing technology. There's an even more ambitious project on the horizon too, something called the Atom Interferometry CERN experiment, often shortened to AICE. If this project actually gets built, it would apply the exact same noise-canceling technique just demonstrated in this small London prototype, but stretched across a vastly larger physical scale. Professor Oliver Buckmuller, the principal investigator leading the AION collaboration at Imperial, described this new result as an important milestone specifically because it demonstrates, under real, messy, imperfect experimental conditions, a key technique that's directly relevant to the next generation of atom interferometer facilities currently being developed internationally, explicitly naming both MAGIS at Fermilab and the proposed AIC facility at CERN as direct beneficiaries of this exact validated approach. If AIC eventually gets approved and constructed, it could end up representing one of the largest quantum physics experiments ever built anywhere on the planet, marking a genuinely new direction for CERN, an institution best known for smashing particles together at incredibly high speeds, rather than gently listening for the faintest possible whispers hidden in ultra-cold atoms. To put the scaling ambition here in perspective, the tabletop prototype used in this specific experiment sits comfortably inside a single university laboratory room, with its 2 atom clouds separated by a distance you could measure in ordinary meters. A full-scale facility like the one AION is ultimately working toward, or the proposed AICE experiment at CERN, would need atom clouds separated by distances measured in hundreds of meters, potentially even kilometers, likely built inside deep vertical shafts or repurposed underground tunnels specifically to shield the delicate atoms from vibration, temperature fluctuations, and stray electromagnetic interference from the surface above. CERN, in particular, already has extensive underground tunnel infrastructure built for its particle collider experiments, which is part of why it's being seriously considered as a potential host site for a future large-scale atom interferometer. The same tunnels originally built to smash protons together at nearly the speed of light could potentially find a second life, housing an instrument designed to listen for the quietest signals in the entire universe instead. Getting from this small, successful prototype to a facility on that scale will likely take years of additional engineering work, funding approval, and careful planning. But this new result is exactly the kind of concrete, published proof of concept that makes securing that kind of long-term investment considerably more realistic. It's worth pausing here to really appreciate why dark matter and gravitational waves are considered such enormous prizes in modern physics, because it helps explain why so much effort and funding is being poured into a technique this specialized and this difficult to pull off. Dark matter makes up roughly 85% of all the matter in the entire universe, based on how galaxies rotate and how galaxy clusters hold themselves together gravitationally. Yet despite decades of dedicated searching using multiple, completely different detection methods, not one single dark matter particle has ever been directly and conclusively identified in any laboratory anywhere on Earth. Meanwhile, gravitational wave detectors like LIGO have already opened up an entirely new way of observing the universe over the past decade, successfully picking up ripples from massive, relatively nearby events like colliding black holes and neutron stars. But there's an entire range of gravitational wave frequencies, particularly extremely low frequency signals, potentially left over from the earliest moments after the Big Bang itself, that existing detectors like LIGO simply aren't built to pick up. The long baseline atom interferometers, like the one being developed through AION, are specifically designed to eventually fill exactly that gap, opening up frequency ranges nothing else currently operating on Earth can access. It helps to understand exactly why LIGO, despite being an incredible piece of engineering in its own right, has this particular blind spot. LIGO detects gravitational waves using laser beams bounced between mirrors spaced several kilometers apart, and that specific physical setup makes it naturally sensitive to relatively high frequency gravitational waves, the kind produced by two compact objects like black holes spiraling rapidly together in their final moments before merging. But gravitational waves theorized to have been produced in the universe's earliest fractions of a second, potentially during a period called cosmic inflation, would show up at frequencies dramatically lower than anything LIGO's mirror-based design can pick up. Atom interferometers work on a fundamentally different physical principle, tracking the quantum behavior of atoms themselves rather than bouncing light between mirrors, and that difference in approach happens to make them naturally well suited to exactly the lower frequency range LIGO can't reach. If facilities like AION, MAGIS, or the proposed AIC eventually scale up successfully, they wouldn't be competing with LIGO so much as filling in a completely different, currently empty section of the gravitational wave spectrum, opening up an entirely new window onto the universe's very first moments that we currently have no way of observing at all. It's also worth being completely honest about exactly what this new result does, and just as importantly, what it doesn't do. Because that honesty is really what separates solid science reporting from pure hype. This experiment did not detect dark matter. It did not detect an actual gravitational wave either. What it did do is prove, for the first time, under genuinely realistic, imperfect experimental conditions, rather than a clean theoretical calculation, that the core noise-canceling technique underlying essentially every serious future dark matter and gravitational wave detector design actually works exactly the way physicists have been hoping and assuming it would for years. That distinction matters enormously because an enormous amount of planned future funding, engineering effort, and international collaboration has been built on the underlying assumption that this specific technique would eventually work as intended once someone actually tested it properly. Now, for the first time, there's real, hard, published experimental evidence directly backing that assumption, rather than relying purely on the theory and simulation. This also connects to a much broader pattern we've been tracking on this channel across quantum physics more generally, the sheer scale of the ambition currently being poured into quantum sensing technology as a whole. It isn't just these atom interferometer projects either. Around this exact same period, other quantum sensing efforts have been making genuine headlines too, with researchers extending the usable lifetime of tiny magnetic quantum particles, called magnons, by nearly 100 times, potentially opening the door toward quantum computers that could eventually shrink down to roughly the size of a coin. Machine learning combined directly with quantum physics has also recently helped researchers discover brand new superconducting materials considerably faster than traditional trial and error methods ever could manage on their own. All of these seemingly separate stories point toward the exact same underlying trend. Quantum technology is rapidly moving out of purely theoretical physics papers and into genuinely working, testable hardware, one carefully validated piece at a time. What's particularly striking is how quickly quantum sensing specifically has moved from a niche academic subfield into something with real, immediate, practical applications well beyond fundamental physics research. The same underlying atom interferometry principles being tested here for detecting dark matter and gravitational waves are already being adapted for far more down-to-earth uses, including navigation systems that don't rely on GPS satellites at all, useful for submarines operating deep underwater, or for backup navigation in the environments where satellite signals get jammed or blocked. Precision gravity measurements using similar ultra-cold atom techniques are also being explored for things like detecting underground mineral deposits, monitoring volcanic activity, or even tracking changes in groundwater levels from orbit. That's part of why government funding agencies and international collaborations have been willing to invest so heavily in getting the fundamental physics right first. A technique proven capable of detecting something as impossibly faint as a hypothetical dark matter field is very likely to find plenty of valuable practical uses long before anyone actually confirms what dark matter is made of. What makes this specific atom interferometer result stand out from a lot of other quantum computing headlines you might have seen recently is exactly how it was tested. Instead of simply claiming impressive numbers under perfect, artificially controlled laboratory conditions, the Imperial team deliberately went out of their way to sabotage their own experiment first, intentionally injecting far more noise than any real system would normally ever generate on its own, specifically to prove their solution could still hold up even under a genuinely worst-case scenario. That's a meaningfully different and honestly more convincing kind of scientific claim than simply reporting your best possible result achieved under the most favorable conditions you could arrange. It's the equivalent of a car company proving their brakes work by deliberately testing them in the worst possible weather conditions imaginable, rather than only showing off footage recorded on a perfectly dry, sunny racetrack. This kind of deliberately harsh stress testing matters enormously in experimental physics, specifically because so many promising ideas that work beautifully on a whiteboard or inside a computer simulation quietly fall apart the moment they meet the messy reality of an actual physical laboratory. Real equipment vibrates slightly. Real lasers drift in frequency over time in ways that are hard to fully predict. Real temperature fluctuations, even tiny ones, can subtly throw off incredibly sensitive measurements in ways a clean theoretical model simply doesn't account for. By intentionally injecting far more noise into their own system than any real detector would likely ever encounter under normal operating conditions, and still successfully recovering a clean signal, the Imperial team gave themselves, and everyone else in the field, watching closely, genuine confidence that this specific noise cancellation approach has real margin built into it, rather than just barely scraping by under perfectly controlled, best-case laboratory conditions that might never actually occur once the technique gets deployed inside a much larger, more complicated real-world facility. Looking ahead, the next real test for this entire approach will be scaling it up from a tabletop experiment sitting inside a university physics lab into something dramatically larger, potentially stretching across entire underground tunnels at facilities like CERN or Fermilab. Longer physical baselines directly translate into significantly better sensitivity when you're using this specific measurement technique, which is exactly why projects like the proposed AICE facility are being seriously discussed as genuinely massive future undertakings, rather than simple, modest laboratory upgrades. If a facility like that eventually gets built and successfully detects a genuine confirmed signal, whether that turns out to be a real dark matter interaction or an actual gravitational wave from the very early universe, it would represent one of the single biggest breakthroughs in the entire history of physics, comparable in genuine significance to the original detection of gravitational waves by LIGO back in 2015. This new result out of Imperial College London is really the first solid, concrete, published stepping stone directly on that specific path. It's genuinely worth sitting with how long a road this actually is, because that patience is part of what makes this story compelling rather than just another overhyped headline destined to be forgotten in a week. LIGO itself, before it finally detected its first confirmed gravitational wave in 2015, had been under development in one form or another since the 1970s, with the actual detector construction taking decades and multiple major redesigns before it finally reached the sensitivity needed to catch anything real. Atom interferometry, as a serious tool for fundamental physics research, is following a broadly similar trajectory: early theoretical proposals, followed by years of incremental laboratory demonstrations proving out individual pieces of the underlying technology, before eventually scaling up toward a facility genuinely capable of making a landmark discovery. This new result from Imperial doesn't guarantee AION, MAGIS, or AIC will succeed in detecting dark matter or ancient gravitational waves, but it does remove one of the specific technical uncertainties that could have otherwise stalled the entire approach indefinitely, which is exactly the kind of unglamorous, methodical progress that eventually adds up to genuinely historic scientific discoveries. If this kind of deep dive into how modern physics breakthroughs actually happen behind the scenes is what you come to this channel for, that's exactly the kind of coverage we're going to keep doing going forward. Subscribe if you want more of it, because most coverage of stories like this either completely skips over the actual technical details entirely, or drowns you in so much dense jargon that the genuinely exciting part of the story gets lost somewhere in the middle. It's also worth remembering that breakthroughs like this one rarely arrive with the kind of dramatic, single-moment reveal you might expect from a movie. Real scientific progress in a field this difficult tends to look exactly like what happened here: a relatively quiet, carefully controlled laboratory result published in a respected journal that most of the general public will never hear about, but that specialists across the entire field immediately recognize as a genuinely important piece falling into place. The eventual detection of dark matter or a primordial gravitational wave, whenever it finally happens, will very likely trace directly back to unglamorous technical milestones exactly like this one, stacked carefully on top of each other over years of patient, methodical work. Drop a comment and tell me honestly, does the idea of using individual atoms to eventually detect a black hole collision that happened millions of years ago sound completely wild to you? Or does it make sense once you actually understand how the underlying technique works? I want to know where this audience genuinely lands on this one. We're going to keep tracking this story closely too, because Between the ongoing AION collaboration in the UK, the parallel MAGES project running at Fermilab, and the proposed AIC facility potentially coming to CERN, there is clearly a lot more of this specific story still waiting to be written over the next several years. I'll see you in the next one.